It also has applications in like computer chips, sending signals in medicine, agriculture, growing plants, maybe even like cellular regeneration. Who knows?
Welcome to the Quantum and Beyond podcast, where I make quantum physics personal to you. On today's episode, we're continuing our series on life in science and beyond, where I am joined by the amazing Elon Price. Her pronouns are she, her, hers, and she is a Ph.D. candidate in plasma physics at Auburn University. Her interests fall at the intersection between plasma science and technology, and I am very excited to learn more about her work with the Magnetized Dusty Plasma Experiment device, along with her commitment to mentorship and advocacy, and of course, a bit of her life outside the lab. Elon, welcome to Quantum and Beyond.
Yes, thank you for that amazing intro. I love it. I love it. I'm
Yeah,
so happy to
absolutely.
be with you on the podcast. This is awesome.
Absolutely, absolutely. And thank you for agreeing to be on in the midst of your busy PhD schedule.
Yeah, it'd be like that.
So just to kind of give some context for the audience, let's say you're with a group of friends who do not study science. How would you describe your research area of magnetized low temperature plasma?
Yes. So I love this question. So I do love talking to my friends about my research, whether they like it or not. So essentially, I'm looking at a weird, like, energetic state of plasma. It's a state of matter. So you probably heard of solid, liquid, gas, but most people have not heard of plasma. I actually didn't hear about plasma until I was in grad school in my master's. And so it's kind of like a different state of matter where you add more energy and then you can get turn a gas into a plasma. But I specifically study low temperature, so not the super hot stuff like the sun, but I study like the other end where it's actually a very low temperature and it makes it easier for us to generate in the lab. So the really, really cool thing about my specific regime of plasma is that I also just slam a huge magnetic field on top of it and hoping that I can basically control the way the plasma and plasma structures behave with magnetism. Low temperature plasma has the most applications in real life. In addition to being really cool science like I'm studying, it also has applications in like semiconductors, so making computer chips. It has applications in signals, sending signals. It has applications in medicine and agriculture, growing plants, maybe even like cellular regeneration. Who knows?
Who knows?
But at the end of the day, there's just a wide range of ways that we can apply this to help people in their everyday lives. And so that really like drew me in. And I decided, okay, I want to look at some weird wiggly structures. That sounds
So actually, that brings up one question, which is how do you make plasma in the lab?
cool. So essentially, you need a gas and you need energy source. And
Mhm.
so we make capacitively coupled plasmas. And so what that means is that we have two plates, and then in between the plates, we put a gas. We use argon because it's like a common gas and it's like cheaper. And then we power the bottom plate to a power supply, and we add power to that plate, and that generates a plasma through a basically a cascade of waves that are between the plates. So you may know about a capacitor because everybody uses batteries, and that's what capacitors are like. And so this is basically a gigantic plasma and a gigantic capacitor, and we're making the plasma in between the capacitor. And so in
Okay.
my lab, and my favorite part about this is that argon is purple. So yes, I get to make beautiful purple structures all day long and take movies of it. And so in my lab, I basically have the vacuum chamber, the gas inside, the capacitor, and then I power it with um, electricity, and then I make a low temperature plasma.
That's very, very cool. And you then control that plasma with magnetism?
Yes. So you can do a lot of cool things with low temperature plasma. My group specifically, my research group, is known for dusty plasma. And so the really cool thing about plasma is there's a lot of physics to be learned. I'll put it like that.
Yeah.
And so when I started actually taking plasma courses, I took a Princeton summer school online. And I was like, wow, there's a lot of unsolved math in this. And I was like, ooh, I like that. I was like, I feel like there's a lot to be developed here, and there's a lot of progress that's being made at the same time. So I basically, through that inspiration, I found this magnet. And this magnet is super, super unique because it's the only one of its kind in the country. And you probably have heard of something like this because it's actually considered an MRI device. So if you ever heard of getting an MRI, it's a similar technology, except that it's more exposed so that we can put the plasma inside. And
Mm.
so it's extremely safe because it kind of is very contained. That's the really cool thing about it, is that the magnet is extremely uniform and it can run for like the longest I've ever run it is like 2 weeks at 2 Tesla, which is a very, very high magnetic field. And so, like a typical MRI that you might get if you had to get a scan, that might be somewhere around 7 Tesla, just talking to my, my bio friends and asking them. So I'm using like 2 Tesla. But if you really want to think about what does that mean, that we're talking about essentially 40,000 times stronger than the Earth's magnetic field. So
Wow, that's crazy.
we have a very strong magnet, to say the very least. We use it's a superconductor, and that's how we're able to achieve this high of a strength. And you have extreme, safety precautions. At when you get to a certain level of Tesla, you have to have, multiple people in the operating room just for safety, because at the end of the day, we're pumping about like almost up to 100 amps of power into the coils so that we could be able to produce this strength of magnetic field. And that's a lot of electricity. And so with that, I'm able to put my chamber inside of that and then look at, now that I apply this magnetic field onto the plasma, what happens. And the work of my group has been basically, they built this magnet the past 12 years. They tried things and they're like, well, that's crazy. Literally, like every single time, they're like, oh, okay, so that's not what we expected to happen.
Which is always actually a good thing in science.
Yes, science!
That's actually what we want.
Exactly, because now your girl's getting her PhD. And I am
Exactly.
one of many PhDs, all because of building this extreme, unique device. Why is it called the magnetized plasma dusty plasma device? This is because, like I said, my group is known for dust. And at the end of the day, dust is much more massive than the particles that make up a plasma. Plasma is made of
Mm.
charged particles. So dust is actually much more massive than a charged particle, and therefore it feels gravity. Something that's mass feels gravity.
It's all about gravity.
And so in order to be magnetized and
Hmm.
look at the effects of how can we control where the dust goes, because dust is actually the biggest problem ever. I never would have thought that in my life, but dust and dusty plasma is actually a huge problem for many, many applications in our daily lives. And so
Hmm.
being able to control how the dust moves, the dust transport, is extremely crucial. And magnets may be able to help us do that better. So basically, in order to magnetize dusty plasma, you have to have an extreme, 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 extreme strength magnetic field. And that's where MDPX was born. And so what
Mm.
they did not
Okay.
expect was to see these wiggly, weird plasma structures that I look at in my research. And so my project actually is looking at the plasma structures themselves and not putting any dust in it at all. So literally looking at how the plasma evolves over time.
Okay. Got you. And so, just to kind of take a step back a little bit, is dust like what we think of every day as far as dust, or does it have a specific meaning in plasma physics?
Yes, I love that question. So actually, the first thing, to take another step back,
Yeah.
is that plasma is not as prevalent on Earth as you might think. And when I say that, I mean like here on Earth, it's not as naturally occurring. We have specific things that we see in nature where we see plasma, which is lightning that you see all the time, maybe, and the northern lights. We also have the sun, but that's, super far away, but that's a big ball of plasma. And then we have flames. Like some people say that fire is plasma. And then when you go to a store, or a restaurant or beauty supply or wherever you go, you might see a neon sign that tells you whether or not it's open. That's a type of plasma, but that's technically like electricity that we generated the plasma from neon gas. So that's not really naturally
Okay.
occurring. So at the end of the day, where's all the plasma? Well, it's everywhere but Earth, basically. And so 99.99% of the universe is plasma. And because we have matter that gets charged, maybe from lunar dust, maybe from asteroids, any kind of dusty particulate type matter that can get charged by radiation. And since plasma is responding to electric and magnetic fields, they couple together and they become dusty plasma. And that makes
Mm,
up a lot of the matter that's in the visible universe. And so being able to understand that also helps with things that we want to do in space. Like, for example, I said lunar dust. Dusty plasma is a huge problem for spacecrafts and for landing on the moon or even maybe building a moon base. Anything we have to do where the dust on the surface could be charged, it can clog our equipment, it can, mess with our suits. I think one of the Mars landers died from dust. Like, so it definitely is a huge problem that I really never thought about until I got really deep into this research and working with this group.